While you exist in this moment, photons from the most ancient galaxy humanity has ever detected traverse another 300 million miles through the cosmic void toward Earth. These particles of light embarked on their journey when the universe itself had existed for merely 280 million years, an epoch predating our planet, predating our star, predating even the magnificent spiral structure we recognize as the Milky Way. We stand at the threshold of an odyssey that will carry us through 2 trillion galaxies scattered across the observable cosmos, each one a cosmic island containing mysteries that challenge our understanding of reality itself. The revelation that transformed astronomy arrived in the depths of 2024, when the James Webb Space Telescope directed its infrared sensors toward regions of space that appeared utterly vacant to previous generations of instruments. For decades, the astronomical community operated under a fundamental assumption. Approximately 200 billion galaxies populated our observable universe. This figure seemed almost incomprehensibly vast, a number that stretched the boundaries of human cognition. Yet Webb's observations shattered this long-held certainty with undeniable evidence. The true census reveals 2 trillion galaxies, a tenfold multiplication of cosmic real estate that fundamentally altered our comprehension of universal structure. Consider the profound implications of this discovery. For every single galaxy astronomers believed existed, 9 additional galaxies were concealed in cosmic shadows, too distant and too faint for detection by earlier telescopes. These hidden populations of galaxies have been radiating their ancient light across billions of years, their photons streaming through the expanding fabric of space-time while remaining invisible to human observation until this technological threshold was finally crossed. The Hubble Space Telescope provided the first glimpses of this hidden cosmic abundance when it executed one of the most ambitious observational campaigns in astronomical history. The Hubble Ultra-Deep Field required 11 consecutive days of exposure time, during which the telescope gathered 800 separate images of a patch of sky so minuscule that if you held a grain of sand at arm's length against the night sky, it would completely obscure the observed region. Within that infinitesimal slice of apparent emptiness, Hubble detected 10,000 distinct galaxies, each one a complete cosmic civilization containing hundreds of billions of stars, untold numbers of planets, and potentially countless forms of existence we will never encounter. The mathematics of this discovery cascade into increasingly staggering proportions. The Hubble Ultra-Deep Field represents merely 1/13 of the entire celestial sphere. When you multiply those 10,000 detected galaxies by 13 million to account for the full sky, the resulting number approaches the 2 trillion galaxy count that Webb subsequently confirmed. But even this calculation proves conservative, because Hubble's optical and near-infrared capabilities could only detect the brightest and nearest members of the galactic population. Webb's superior infrared vision penetrates deeper into cosmic time, revealing galaxies whose light has been stretched from visible wavelengths into the infrared spectrum by the expansion of the universe itself. Each of these 2 trillion galaxies contains its own population of stellar objects. If we assume a conservative average of 100 billion stars per galaxy, we arrive at a total stellar population of 200 sextillion stars in the observable universe alone. To comprehend this magnitude, consider that this number exceeds the total count of sand grains on every beach across Earth's entire surface. More stars exist in the observable cosmos than accumulated particles of sand have been weathered from rock and deposited along every coastline throughout our planet's geological history. Yet this overwhelming abundance of galaxies represents only what light has had time to reach us. The observable universe constitutes a finite bubble of space whose radius is determined by the speed of light and the age of the cosmos. Beyond this observational horizon lies potentially infinite space, containing potentially infinite additional galaxies, forever beyond the reach of our detection because the expansion of the universe prevents their light from ever reaching Earth. We inhabit one small region of what may be an endless cosmic ocean, and the 2 trillion galaxies we can observe represent merely the local neighborhood of something vastly more extensive. Within this neighborhood, our own Milky Way galaxy belongs to a gravitationally bound collection known as the local group. This cosmic family contains more than 54 galaxies distributed across approximately 10 million light-years of space. The three dominant members of the local group exert gravitational influence that shapes the motions and fates of all smaller members. Andromeda reigns as the largest galaxy in the local group, a spectacular spiral system containing over 1 trillion stars distributed across 220,000 light-years. This galactic giant possesses roughly twice the stellar mass of our Milky Way and displays a distinctive spiral structure visible to the naked eye from Earth's surface as a faint smudge in the constellation Andromeda. But Andromeda is not a stationary object in cosmic space. The galaxy rushes toward us at 68 miles per second, locked in a gravitational dance that will culminate in collision approximately 4.5 billion years hence. Our Milky Way occupies the second position in the local group hierarchy, with current estimates suggesting a population of 300 billion stars distributed across 100,000 light-years. Our solar system resides approximately 26,000 light-years from the galactic center, positioned safely within the Orion Arm, one of several spiral structures that give our galaxy its characteristic pinwheel appearance when viewed from external vantage points. This location in the galactic suburbs may have proven crucial for the development of complex life on Earth, as the galactic core regions experience higher rates of supernovae and other energetic phenomena that could prove detrimental to biological evolution. Triangulum, the third major member of the local group, presents a spiral galaxy approximately half the size of the Milky Way, with stellar populations estimated around 40 billion stars. Despite its smaller stature compared to its massive neighbors, Triangulum exhibits one of the highest star formation rates in the local group, creating new stellar objects at nearly twice the rate observed in the Milky Way. This vigorous stellar genesis illuminates Triangulum with brilliant blue regions where massive young stars pump enormous quantities of ultraviolet radiation into surrounding gas clouds. Surrounding these three dominant galaxies orbit dozens of smaller satellite systems, many of which circle the Milky Way like cosmic attendants. The large and small Magellanic Clouds represent the largest and most prominent of these satellites, visible to observers in Earth's southern hemisphere as fuzzy patches of light that ancient cultures incorporated into their mythologies and navigation systems. The large Magellanic Cloud harbors approximately 30 billion stars, while its smaller companion hosts roughly 3 billion stellar objects. This entire local group structure occupies a peripheral location within a vastly larger cosmic architecture known as the Laniakea Supercluster. This immense structure encompasses roughly 100,000 galaxies distributed across 520 million light-years, a distance so vast that light requires over 500 million years to traverse from one boundary to the opposite edge. The Hawaiian name Laniakea translates as immeasurable heaven, an appropriately poetic designation for our cosmic address at the grandest scales we can measure. All galaxies within Laniakea, including our local group, participate in a massive gravitational flow toward a mysterious region astronomers designate as the Great Attractor. This cosmic anomaly, located approximately 250 million light-years distant, possesses the gravitational mass of tens of thousands of galaxies and pulls our entire local structure toward it at velocities exceeding 1,000 miles per hour. Yet simultaneously, the expansion of space-time itself pushes most other galaxy groups away from us, creating a cosmic treadmill effect where some destinations grow closer while others recede forever beyond reach. The Milky Way's role as gravitational predator has been unfolding for more than 10 billion years. At this very moment, our galaxy actively consumes at least 2 smaller galactic systems through violent tidal disruption. The Sagittarius dwarf elliptical galaxy undergoes gradual disintegration as our galaxy's gravitational field tears it apart, leaving behind streams of liberated stars that wrap around the Milky Way like cosmic ribbons. Meanwhile, the Canis Major dwarf galaxy has been so thoroughly obliterated that astronomers only discovered its remnants in 2003, when careful analysis of stellar populations revealed the scattered debris of what was once a cohesive galactic structure. This process of galactic cannibalism operates through tidal forces analogous to ocean tides on Earth, but operating at scales that dwarf terrestrial phenomena. Just as the moon's gravity raises oceanic bulges on opposite sides of our planet, the Milky Way's enormous gravitational field creates stellar tides that stretch and distort smaller galaxies. individual stars get stripped away from their parent galaxy and scattered into the Milky Way's outer halo, where some eventually settle into stable orbits, while others are ejected entirely into the dark void between galaxies. Forensic analysis of stellar populations provides evidence for this ongoing consumption. Astronomers can identify which stars originated in destroyed galaxies by analyzing their chemical compositions and orbital characteristics. Stars from the Sagittarius dwarf exhibit distinctly different abundances of heavy elements compared to stars born within the Milky Way, providing chemical fingerprints that reveal their foreign origins. This cosmic archaeology allows scientists to reconstruct collision events that occurred billions of years ago. The disruption of these satellite galaxies triggers cascading consequences throughout the Milky Way. As gas clouds from the Sagittarius dwarf collide with material in our galaxy's disk, compression and heating ignite accelerated star formation in the spiral arms. The death of one galaxy paradoxically feeds the birth of countless new stars in another, demonstrating how cosmic violence and creation remain intimately intertwined. The Large and Small Magellanic Clouds face similar fates. These two prominent satellites currently reside approximately 160,000 light-years from the Milky Way's center, but orbital calculations reveal they follow unstable trajectories. Both Magellanic Clouds will eventually collide with and be absorbed by the Milky Way within the next 2 billion years. When the Large Magellanic Cloud finally merges with our galaxy, the collision will trigger spectacular bursts of star formation, illuminate the night sky with brilliant nebula, and potentially activate the supermassive black hole lurking at our galactic center, transforming it into a quasar capable of outshining entire galaxy clusters. This galactic cannibalism represents common behavior throughout the universe. Andromeda has consumed even more aggressively than the Milky Way, with astronomers identifying the remnants of at least 10 different dwarf galaxies scattered through Andromeda's outer regions. The evidence suggests Andromeda devoured most of these victims within the last few billion years, and the ancient meals remain visible as faint streams of stars stretched across hundreds of thousands of light years. A predictable pattern emerges throughout cosmic history. Larger galaxies grow by consuming smaller systems, which had previously consumed even smaller galaxies in turn. This cosmic food chain has operated since the first galaxies assembled more than 13 billion years ago, with each generation of galactic mergers building progressively more massive structures. But this local cannibalism represents merely a prelude to the ultimate collision already underway. In 4.5 billion years, the night sky will transform into something unrecognizable to modern eyes. Andromeda, our nearest large neighbor, races toward the Milky Way at 68 miles per second. While this velocity seems modest compared to light speed, at cosmic scales, it represents an inexorable collision course between two freight trains of galactic mass. The impact is confirmed, calculated, and will completely reshape both galaxies in the most violent event our cosmic region will experience. The Hubble Space Telescope definitively resolved questions about this collision in 2012 by measuring Andromeda's tangential motion across the celestial sphere. For decades, astronomers knew Andromeda approached us, but they couldn't determine whether the trajectory would result in direct impact or near miss. Hubble's precise astrometric measurements revealed the terrifying truth. Andromeda aims directly at the Milky Way's heart with no possibility of avoidance. When galaxies collide, the event differs dramatically from solid objects smashing together. Galaxies consist primarily of empty space, with typical stellar separations measuring approximately 25 trillion miles. The probability of any two individual stars physically colliding during the merger approaches effectively zero. Instead, the collision manifests through gravitational interactions that prove far more dramatic and chaotic than simple physical impacts. The merger will unfold across hundreds of millions of years, beginning with the outer edges of both galaxies warping and stretching under mutual tidal forces. Massive gravitational stresses will fling entire star systems out of their parent galaxies into the dark void between them. Some ejected stars will carry their planetary systems along, creating orphaned solar systems that will drift through intergalactic space for the remainder of cosmic history. As the galactic centers draw closer, their central supermassive black holes will begin a deadly orbital decay. The Milky Way's black hole contains approximately 4 million solar masses, while Andromeda's central engine weighs in at roughly 100 million solar masses. When these gravitational monsters finally merge, they will generate gravitational waves of such intensity that civilizations billions of light-years distant could detect the space-time ripples. The collision will ignite the most spectacular fireworks display in cosmic history. Gas clouds from both galaxies will collide and compress, triggering massive bursts of star formation that will illuminate the combined system with the light of billions of newly born stars. New stellar objects will form at rates 10 times faster than current levels in either galaxy. Earth's fate during this cosmic catastrophe depends significantly on chance. Computer simulations suggest roughly 50% probability that our solar system will be flung 3 times farther from the galactic center than our current position. A 12% chance exists that we will be ejected from the merged galaxy entirely, sent wandering through the darkness between galaxy clusters. If humanity or its descendants still exist when this collision begins, they will possess front-row seats to observe the merger unfolding over millions of generations. The night sky will gradually fill with increasing numbers of stars as Andromeda grows larger and brighter. Eventually, the approaching galaxy will dominate the entire celestial sphere, a spiral of stellar fire stretching from horizon to horizon. The final product of this cosmic catastrophe will be a giant elliptical galaxy astronomers have already nicknamed Milkomeda. This merged system will rank among the largest galaxies in our local supercluster, containing the combined mass of both progenitor galaxies and displaying the characteristic elliptical morphology that results from major mergers. Yet even this ultimate collision pales in drama compared to certain galaxies that have already died in ways that defy explanation. These cosmic mysteries challenge every model of galactic evolution astronomers have developed. Among these enigmatic relics are so-called ultra-diffuse galaxies, immense structures with sizes rivaling the Milky Way, but containing only a fraction of its stars. Their luminous content is so scant that millions of these galaxies are barely visible, even to our finest telescopes. Some seem to lack the gravitational signatures of dark matter entirely, a finding that has shaken the very foundations of cosmic theory. The very existence of dark matter-deficient galaxies hints at intricate formation mechanisms, immense gravitational interactions, or perhaps the fingerprints of cosmic processes we have yet to imagine. Ultra-diffuse galaxies float throughout clusters ghostly, ephemeral, shaped by galactic tides and perhaps destined for disintegration, their stars streamed away by relentless gravitational pulls. Equally mystifying are the massive elliptical galaxies whose bright centers have been observed to suddenly quench all star birth. These so-called red and dead galaxies once blazed with the energy of countless newly forming stars. Yet today, their pale, ancient starlight tells the tale of abrupt and mysterious endings. It appears that the very act of fierce star formation might trigger powerful galactic winds, spewing superheated gas far into intergalactic space, bleeding galaxies dry of the coolant necessary for stellar nurseries. Or perhaps these endings are dictated by the voracious appetites of supermassive black holes at their centers, behemoths capable of ejecting jets and winds so ferocious they heat or dispel potential star-forming clouds across entire galaxies. One thing is clear: galaxies live, transform, and die in countless ways, sculpted by the invisible hands of gravity, stellar life cycles, and the often unpredictable extremes of the cosmos. To fully appreciate the diversity that exists among 2 trillion galaxies, one must wander the cosmic landscape from the smallest dwarfs to the largest giants, from spirals to ellipticals to chaotic irregulars. Magnificent grand design spiral galaxies, like our own in Andromeda, trace graceful arms of stars, gas, and dust swirling outward from bright central hubs. These arms serve as highways for stellar creation, driven by gravitational waves within the galactic disk compression waves that birth stellar nurseries where massive stars burn blue and brief, shooting their ultraviolet energy across spiral arms, lighting up clouds with glowing nebulae. Yet not all galaxies exhibit such symmetry. Some, like the Large Magellanic Cloud, appear irregular and disrupted, shaped by recent interactions, mergers, or gravitational encounters with larger galaxies. Elsewhere in the universe, elliptical galaxies dominate cluster cores, appearing featureless and filled almost entirely with old red stars. The absence of gas and dust, and thus the near cessation of star formation, gives these galaxies their ghostly glow. Ellipticals can appear in sizes ranging from diminutive dwarf ellipticals to giants containing tens of trillions of stars, often born out of the apocalyptic mergers of spiral galaxies. When two spirals of similar size collide and merge, the ordered motion of their stars shatters. The resulting system is a rounded, more chaotic mass, slowly settling into the shape and serenity of an elliptical galaxy over billions of years. Nearby, the smallest galaxies lead lives of quiet struggle. Dwarf spheroidal galaxies, such as Sculptor and Fornax, contain only a few million stars each, often orbiting as satellites around larger hosts. These dwarfs are rich in dark matter, their meager luminous mass unable to resist the tidal forces of their gargantuan neighbors. In their orbits, they are slowly stretched, torn, and ultimately consumed, their stars dribbling out as faint rivers of light, contributing to the growing halos of their massive companions. The fate of the smallest galaxies is often to vanish, their existence written only in the trajectories and chemistries of a few outlier stars. But the story of galaxies does not stop at mere numbers or visible features. Each one is a theater in which cosmic processes of unimaginable scale and power unfold. Within a typical spiral's arms, massive molecular clouds, repositories of gas and dust, hundreds of light years across collapse under their own gravity, fragmenting into clusters of stars. Newborn stars ignite, and the most massive among them unleash stellar winds and supernova explosions that sculpt, compress, and sometimes disrupt their natal clouds, creating regions of breathtaking beauty and violent turbulence. Inside galactic hearts, especially in the largest systems, lie the most enigmatic engines known to science: supermassive black holes. Ranging from millions to tens of billions of solar masses, these gravitational anchors dominate the central regions. When galaxies merge, their central black holes spiral together as well, creating gravitational waves that shake the very fabric of space-time. In their most active phases, these behemoths secrete swirling disks of gas, powering quasars, cosmic lighthouses visible across billions of light years, capable of outshining all the stars in an entire galaxy. Quasars are the beacons of the early universe. Many of the most distant galaxies found by modern instruments host such active nuclei, shining forth with relativistic jets and X-ray outbursts, blazing a trail through cosmic history. Their light gives us glimpses of galaxy formation mere hundreds of millions of years after the Big Bang, revealing the rapid assembly and collapse of matter under inexorable gravity. As astronomers peer ever deeper, the diversity of galaxies across cosmic time becomes clear. In the first billion years, galaxies appeared smaller, more chaotic, bursting with the fire of unbridled star formation and frequent collisions. Over time, they grew through mergers, accreting matter and neighboring systems. Some became elegant spirals, settling into whorled arms of star and dust. Others became elliptical giants, exhausted by centuries of cosmic violence. In vast clusters, galaxies congregate in thousands of massive central elliptical galaxies dominating, while the faint light from myriad dwarfs delineates the invisible web of dark matter binding the cluster together. This cosmic web is the ultimate scaffold of the universe. On scales of hundreds of millions of light years, galaxies are not distributed randomly, but gather along filaments and sheets in a structure reminiscent of neural networks or spider silk. Between these filaments lie immense voids, regions hundreds of millions of light years wide containing only a sparse handful of galaxies. Gravity threads the web, and as the universe ages, the richest clusters draw more and more galaxies to them, while emptier voids grow yet more desolate. The formation of this web traces its origins to the earliest moments after the Big Bang. Tiny quantum fluctuations in the primordial soup of energy and matter grew over time, seeded by dark matter, pulled together by gravity. Regions with slightly more dark matter attracted more material, snowballing into filaments, sheets, and knots, the framework along which galaxies now congregate. Today, supercomputer simulations reproduce this web in astonishing detail, matching the cosmic landscape as mapped by the Sloan Digital Sky Survey and other ambitious projects. Yet, the universe remains in motion. Every day, clusters draw nearer to cluster, galaxies merge or pass, and lone dwarfs are ensnared by the gravity of giants. The observable universe, already a sphere 93 billion light-years across, grows with every moment, new photons arriving, carrying news from unimaginably distant worlds. But even as we learn more, the expansion of space creates a cosmological horizon, a boundary beyond which no new light will ever reach us, isolating distant galaxies one by one as they vanish from view. Their light stretched into oblivion by the persistent acceleration of the universe's dark energy. Dark energy, a property more alien than any black hole or galactic collision, constitutes 70% of the universe's energy density. Its nature remains one of the ultimate puzzles. This force, whatever its origin, propels galaxies apart at ever-increasing speeds. Eventually, the accelerating expansion ensures that only the remnants of our local group, or its future echo Andromeda, will remain visible, an island of stars adrift in an infinite black sea. Everything else will speed beyond sight, beyond interaction, beyond knowledge. For now, though, we inhabit a time when the entire observable universe can be studied. Superclusters, filaments, voids, clusters, satellites, all can be mapped, dissected, and compared. From the tiniest, dimmest dwarf to the largest elliptical giants, the zoology of galaxies is a living record of cosmic evolution, chaotic, violent, beautiful, and serene. Contemplate the distances involved. The most distant galaxy, GN Z11, lies more than 32 billion light-years away. The light we see began before our solar system was even a cloud of stardust in the Milky Way's arm. Our own radio whispers messages from Earth's technology have traveled only 100 light-years in the vast ocean of cosmic night. To travel between galaxies using current technology is a feat orders of magnitude beyond anything achieved by humanity. And yet, thanks to the speed of light, every new observatory lets us, for a moment, cheat cosmic distances and peer into the deepest past. Within each galaxy, there are the seeds of future mysteries. Star clusters orbit their hosts in fantastic loops. In the Milky Way's halo, the ancient globular clusters, compact balls of up to 1 million stars, circle steadily, relics of the galaxy's earliest days. Some may have formed in primordial dwarf galaxies long since consumed or disrupted. They carry in their star's chemistry a fossil record of a time when the universe was a fraction of its present age. At the centers of clusters, galaxies interact in spectacular ways. Tidal forces distort spirals into long, sweeping tails, flinging stars and gas into intergalactic space. In some clusters, such as the Coma cluster, galaxy collisions happen at high speeds, and the hot gas between galaxies emits X-rays heated to tens of millions of degrees by these colossal, slow-motion car crashes. And in special places like the famous antenna galaxies, we witness collisions caught in the act. Here, dust and gas are compressed and shocked into tumultuous regions of vigorous star creation. Superstar clusters, dense knots of hot, young stars ignite, setting the stage for waves of future supernovae that will enrich future generations of stars and planets with heavier elements. Meanwhile, not all galaxies are doomed to extreme violence or ultimate quiet. Some, known as green pea galaxies, boast rare, intense bursts of star formation relative to their size, while others dance in elaborate orbits around each other, tidally twisting their shapes, but never fully merging. In the peripheries, rogue planets, orphaned by disrupted systems, wander the void, and faint galaxies flicker almost undetectable against the background. The universe is a theater, and galaxies are its troops, each performing an act across billions of years, from humble beginnings in clouds of hydrogen to complex, mature systems, and ultimately to dissolution or rebirth. Humanity, standing on its minuscule planet in the quiet suburbs of a typical spiral, gazes upward and outward, gathering fragments of these acts through telescopes, data streams, and mathematics. We have named and mapped the brightest beacons, the Andromedas, Triangulums, the spectacular Sombrero and Whirlpool, the Cartwheel with its ring of newborn stars, and active galaxies like Centaurus A, with its jets visible in X-rays and radio. We have cataloged dwarfs by the dozens in our sky, each a candidate for future cannibalism or clues to primordial star formation. But the vast majority, the dimmest and farthest, remain anonymous, unreachable, perhaps unknowable forever, yet certain to be worlds of wonders and stories without end. As we look to the future, New generations of telescopes, ground-based giants with mirrors the size of tennis courts, and next-generation space observatories will stretch the boundaries of what we can know. Each advance reframes our understanding, reveals yet more galaxies where once we counted emptiness, and sharpens our sense of humility. For in the act of surveying 2 trillion galaxies, we catch a glimpse not only of the universe's history, but of its inexhaustible capacity for invention and beauty. So, as the photons of ancient stars continue to arrive, as simulations and theories weave fuller narratives of galactic birth and demise, as human curiosity persists generation after generation, the story of the cosmos unfolds slowly, inexorably, always just beyond the reach of final certainty, yet boundless in the wonder it inspires.